Hello, in this video we are going to look at three different ways of solving some differential equations. In our math class we have already talked about separating variables to solve differential equations, but we will take a quick review as we go through this video. We will also talk about solving differential equations with exact factors, and then we will move from there to talk about how to find an integrating factor for a differential equation. It is important that you would have covered integration by parts, substitution, and trigonometric functions, and you would have solved differential equations by separating variables, which is something we did in P3, and you should have also mastered your implicit differentiation. Okay, as we go through this video, what I need you to do is, each time there is a problem to solve, I would hope that you pause the video. When there is a problem, you try the problem first, and then you see how I get the solution. So, okay, let's start with a quick reminder of solving differential equations by separating variables. So, pause the video a little bit and solve this differential equation. X squared dy on dx equal y plus 1. I hope you pause the video and try to solve this equation. So what we do here, we have to separate the variables. Remember, we said that you treat this dx as if it was a term in this equation. This means you send out dx, so you send all the x terms on one side, on the right hand side, and send all the y terms on the left hand side, including dy. So, and then you integrate. After you've sent those terms to one side, you then integrate, and so you have your natural log of y, 1 over y plus 1 dy, integral of 1 over y plus 1 dy is the same as natural log of the absolute value of y plus 1, and the integral of this will be negative 1 over x plus your constant c. Remember to always add the constant c. The next step is we will have to substitute these initial conditions. When y is 0, x is 1, to look for the value of c. And so we'll get c as 1. Then we can put our c as 1 here, and then we simplify. Remember, you have to make the final result look much simpler. So you get y equal that, e raised to the power 1 plus 1 over x minus 1. Here is a second differential equation. Pause the video and try to solve this one as well. So, in this differential equation, remember this, again, you have to send all the y terms on the left hand side and all the x terms on the right hand side, then use your integral sign. Remember that e raised to the power x plus y is the same as e raised to the power x times e raised to the power y. So, we can send e raised to the power y on the left hand side and e raised to the power x on the right hand side. Okay, and then we integrate that. Then you should get this, because you don't have any initial conditions for this problem, so your solution will remain what it is. Or we use the same initial conditions that we had here. So now also pause the video and try to solve this other differential equation. Pause the video for a while and try to solve it. Now, you remember, if you look at this differential equation, it may be very hard for you to separate the variables. right? You cannot separate the variables. This means you cannot send all the x's on one side and all the y's on the other side. But if you look at this left-hand side, you will see that this left-hand side is the derivative of x squared y. So if you want to differentiate x squared y, you first leave your x squared, you differentiate y, you will have x squared dy on dx, and then you leave your y, you differentiate x squared, you get 2xy. So that is what we have done. So the left hand side is just the derivative of x squared y. And so we can therefore write the differential equation as d on dx of x squared y is equal to 3 sine x. And then we can now integrate. So x squared y will be 3 times integral of sine x dx, giving us that. And so we can substitute our initial condition, which is here, x0, y1, to get our value for c. And therefore, our final result is what you have there, x squared y equal 3 minus 3 cos x. You can simplify in any other way you want. Solve this other differential equation. Again, you need to pause the video and try to solve this other differential equation. Again, you notice that the left-hand side is an exact derivative. It may be difficult to find for this other one, but you can notice it there. So you still put it there, d over dx of the whole thing inside is equal to 1 over x, and then you arrange and integrate. Find your c, and then you can express in terms of y equal f of x. Now, we are able to solve these differential equations because the left-hand side was exact derivative. These two that we have just solved, the left-hand side of these two equations are exact derivatives. But in most cases, when you are solving differential equations, you will not encounter exact derivatives. For example, this one, what can we do to make the left-hand side of this one an exact derivative? It's not an exact derivative, so what can we do to make it an exact derivative? Think of something you can multiply all through that will give you an exact derivative. Maybe x, yes, if you multiply all through by x, and so you will have something like this left hand side, you have x, y, so you have x dy on dx plus y times dx on dx, which is 1, will give you that left hand side. So after expressing it as derivative of xy, we can then solve that. We call the factor x that we have multiplied all through here an integrating factor. We have multiplied all through this equation by x, so we call the x an integrating factor of this differential equation, which we can solve as we have here. I have already explained that, so just showing how to solve it again. So we have to find a way to find integrating factors. How can we find an integrating factor? For the last problem, it was very easy to find, to just use intuition to get, but we have to find a rule that you can use to find integrating factors. Because it is not always an obvious thing to find. So let's consider any differential equation, a general differential equation, dy on dx plus y times a function of x, p of x, equals some other function of x, q of x. Now, remember that the coefficient of dy on dx here must be 1. The coefficient of dy dx is 1. And then we can multiply by some factor, f of x, some integrating factor, f of x. Then we will be able to find f of x. If we multiply all through by f of x, we have what we have here. And then what we now know is that the left hand side, let me arrange this, the left hand side here should be an exact derivative of something, right? So the first term is the term when we differentiate y times f of x. So if you differentiate y times f of x, then you use the product rule. So you first leave your f of x constant, you differentiate y, you will get dy over dx. So the second term here should be what? The second term should be the next term. So first you leave f of x, you differentiate y, you get dy over dx. So you should now leave y, then you differentiate f of x. So the second term should be f prime of x, right? So you have d over dx of this should be this plus y f prime. So f prime here, f prime must be equal to f of x times p of x, right? F prime of x should be f of x times p of x. So p of x should be f prime of x all over f of x. Now we can use this last equation to find f's of x. So we can integrate all through. Integral of p of x dx should be integral of f prime of x all over f of x dx. Now what should this integral be? This integral, as we already know, is the log of f of x, absolute value of f of x, right? So integral of p of x dx should be log of f of x. In this case, we haven't added the c. We just ignore the c for now. And so we can find f of x. F of x will be e raised to the power integral of p of x dx. So this is our integrating factor. We are able to find our integrating factor. So it's a very important factor that you need to remember. So that is what we use to find the integrating factor. The integrating factor is e raised to the power integral of p of x times dx. Always remember that the coefficient of dy over dx should be 1. And then you should have y times p of x here. So if you have to solve this differential equation, you need to arrange it such that the coefficient of dy over dx should be 1. And then this one should be y times something, some function of x, right? So p of x should be the coefficient of y here, which is 3 over x, right? P of x is 3 over x. And then your integrating factor will just be e raised to the power integral of 3 over x dx, which is e raised to the power 3 ln x. Now we can arrange it and make it much simpler. 3 ln x is the same as ln x cubed, right? And e raised to the power ln x cubed should just be x cubed. So that will just give us x cubed. So our integrating factor in this case is x cubed. So we just multiply all through by x cubed. And then now we realize that the left hand side is an exact derivative. It will just be d over dx of the integrating factor times y. And so we can solve it to get our y as a function of x. Example 2. Please pause the video and try to solve example 2 in this case. dy on dx plus y cot x equal cosec x. Our integrating factor will just be e raised to the power integral of cot x, which is e raised to the power natural log of sine x, which is just sine x. And so our left hand side will just be the derivative of this thing. Of sine x cot x. Yeah. Derivative of sine x times y should be 1. And so we can find our integral now. It is much easier to find. Okay, you can try. Also pause the video at this stage and try these 2 problems using the integrating factor. Okay, you should get, for the first one, y equals cx minus 1 over 2x, where c is your constant of integration. For the second one, you should get y equal to x minus 1 e raised to power x plus 2 e raised to power negative x. There is no c in the second one because you have your initial conditions. Okay, you should try exercise 24 in your books, question 1 to 9. Thank you.